I guess I can get started. I can introduce myself. Hi, I'm Brandon. I am a senior astrophysics major. I'm an undergrad at MSU. For the reason why I'm here is I gave a talk at the APS DPF conference this past summer. Austin saw my abstract and thought it was cool and thought it'd be relevant for you guys, so he invited me to come talk. This past summer, I actually transitioned away from the RNN project. I started a new one, and that was handed off to Nathan Willey, and so I offered for him to co-present. That way he would get an opportunity to talk about some of his own research instead of me just saying for him. So we're going to be co-presenting today. Yeah, I think that's it. Do you want me to get started? Michael, Austin, do you want me to get started?
Sorry there, I had trouble getting the mouse over to the other screen. Yeah, so you can get started, yeah.
Okay.
We're at a pretty normal size for us right now, about 7 virtual and another 5 or 6 or so in person, so I think we're good to go.
Okay, a quick question on my end. Would you like me to run straight through or would you like me to pause every so often for questions?
How about we maybe just go straight through and then wait for the end, unless someone has a really burning question, maybe.
Okay, that sounds good. Okay. All right, yeah, so today Nathan and I are going to be talking about using recurrent neural networks as a tool for IceCube-Upgrade Reconstructions. So to start out, we need to start out with neutrinos. These are particles, they are leptons as part of the standard model. There's 3 different flavors of neutrinos associated with the other 3 leptons, electrons, muons, and taus. They can be created in processes like beta decay, where a proton or neutron in an atom will change from one to the other and it will release some sort of electron or positron and then a corresponding neutrino. It can be created in high energy events like supernovae and compact object mergers. So this, for example, is the Crab Nebula. It's a very famous supernova. Can also be created in nuclear fusion. So this here is a diagram of the PP chain, which is a process by which the sun generates helium from hydrogen, and that releases 2 neutrinos. So neutrinos are quantum particles and they go undergo oscillations. They propagate in mass eigenstates, but they're measured in flavor eigenstates. So for example, this mass eigenstate here has this corresponding breakdown of different flavor ratios that correspond to that eigenstate. And then these mass eigenstates constitute a mass hierarchy. It's not currently known if the mass hierarchy follows a normal ordering or inverted ordering. So normal ordering would be 1, 2, 3 increasing, and inverted will be 3, 2, 3, 1, 2 increasing. The absolute scale of the mass ordering is not super well constrained. There are upper limits on the order of like 1 GeV or 1 EV or 1/10 of an EV. But the differences between these mass eigenstates are on the order of like 10 to the minus 5 EV. So there's several orders of magnitude in range where they could be. Neutrinos are pretty antisocial. They really don't interact with matter very much. In some ways, it's good news because it means that they can travel to Earth undisturbed from their source, and they serve as a great pointer to their source, assuming we can figure out where they're coming from accurately. The bad news is that since they're so unlikely to interact with anything on the way here, they're also very unlikely to interact with anything when they get here. So most of them are just going to fly straight through Earth, and we're never going to see them again. One of the reasons for this is that neutrinos only really interact via the weak force. They're electrically neutral, they're leptons, and they're nearly massless, something like 500,000 times lighter than electrons or more. And that rules out the other 3 fundamental forces. And so they interact via the weak force, but that is an incredibly short range, something on the order of like 10 to the minus 3 femtometers, which is like 0.1% of the proton radius, which is really small. So at that point, you basically have to hit it head on. And that's also incredibly likely. And so to demonstrate that, I built a scale model where you size everything up by a factor of 1 trillion. So that would be 1 picometer going to 1 meter. So on this scale, the radius of the proton is about the thickness of some sort of like plastic credit card or ID card. The radius of an electron is about the thickness of a nickel. The Bohr radius, which would be like this rough size of a hydrogen atom, is about the size of an SUV. And an upper limit on the neutrino charge radius is something like the size of a Streptococcus bacteria, which is really small. So on this scale, you can fit something like 10 to the 13 neutrinos in this circle of a Bohr radius. And only about a million of them or so will have a direct collision with either the proton or the electron. Now, this is a classical example. In practice, things are much more complicated. Not all neutrinos are going to be flying through an atom at any given time. This isn't accounting for oxygen atoms that you'd also see in water or ice. The actual cross-section is technically energy dependent, so there are a lot more complicating factors, but I think this gives you a good idea of why neutrinos are so uninteractive. So in order to compensate for that, you need to build a really big detector, and that is where IceCube comes in. It's a neutrino detector situated below the South Pole, about 1.5 kilometers to 2.5 kilometers down. It uses a cubic kilometer of Antarctic ice, hence the name. IceCube detects Cherenkov radiation from neutrino interactions. So what will happen is that you'll have a neutrino come in and interact with the ice, and that will produce some shower of hadrons or leptons. And what will happen then is that those secondary particles will move incredibly fast, so fast that they actually exceed the speed of light in ice, which is a little bit slower than the absolute vacuum speed of light. And that creates something akin to a sonic boom, but with light. And that produces this special bluish kind of light called Cherenkov radiation. So the ice is instrumented with 5,160 digital optical modules, which we abbreviate as DOMs. And they're situated on 86 different strings, so you get 60 DOMs each. They're separated vertically in the main section of the detector by 17 meters, and then the strings are separated horizontally by 125 meters, where the spacing was optimized for high energy astrophysics neutrinos. Each string is basically just a really long cable that contains all the electronics that connect the DOMs to the surface slab and with each other. And then the primary information that we get from each detection, which we call hit, we know which PMT was triggered, we know what time the PMT was triggered, and we know what charge was collected in the PMT, which is a proxy for the intensity of the light, how much light is actually collected. So to go into a little bit more detail about the DOMs, each DOM contains a downward facing 10-inch PMT with a gain of approximately 10 to the 7. The glass pressure housing around the outside keeps them structurally stable at low temperatures and high pressures that you'd find under 1.5 kilometers of ice. And the penetrator up here at the top carries all of the wiring that connects the DOM to the string. So here's a schematic of a DOM, a actual picture of what the DOM looks like. So this is a DOM on a cable in a harness. You can see the PMT down here at the bottom with the glass pressure housing and the penetrator that connects it back up to the string. And then on the left here is a sample of what kind of raw data we would be getting out of the DOM. So for this specific PMT, we would get something like this, where it's a measurement of the voltage or the current through the DOM as a specific time, which goes back to the information that I talked about in the last slide. There's a second specific portion of the detector called DeepCorel. It's the central area that is a higher instrument density. So the DOM vertical spacing is decreased from 17 meters to 7 meters. And then the string spacing is decreased from 125 meters to 72 meters on average. It consists of 8 strings, where most of the DOMs have a higher quantum efficiency by about 35%. And then the energy resolution of DeepCorel has a lower limit of about 10 GeV. Some analyses will quote down to about 5 GeV, depending on how good is good enough for your reconstruction. So just to provide here's a schematic of DeepCorel, and then just a more practical image on the left of some downgoing event that interacts up here and then releases light as it travels down. And then as it gets into DeepCorel, into the higher instrument density, you get a lot more light reflected. And at this point, I need to start talking about the kind of signatures that we see in the detectors. Some terminology notes. CC is referring to charge current, which is an interaction mediated by the W boson. And NC is referring to neutral current mediated by the Z boson. And then there are different abbreviations for the neutrinos are nu E, nu mu, and nu tau for the different flavors. So the two main types of events that we get in IceCube are tracks and cascades, which this diagram is called showers. Tracks occur from charge current mu events, because what will happen is that it will interact and release a muon. This muon has a relatively long decay lifetime, so it has time to travel through the detector and release light as it goes. We get cascades from CC nu E events, where it produces an electron, but that's quickly captured by an atom. And so the event is essentially point-like, and you just get this roughly spherical distribution of charge. NC events don't actually change anything with the particle identities. It's just a transfer of energy and momentum. So that is also essentially point-like, happens at a single point. You can also get rare double bang kinds of events with high energy nu tau. So this would be like the tau interacting up here, and then the tau will travel some distance in the detector and then decay again, which you get like a second cascade. Depending on the energy of the tau and the decay channel at lower energy, you can get different signatures of events, but that's a little more specific and beyond the scope of this presentation. IceCube also has struggles with low energy reconstructions for a couple of reasons. First is that the low energy events don't produce very much light. That means you're not going to detect very much light, and this lack of information leads to poor low energy reconstructions. Another difficulty is that the muon track length is energy dependent, where higher energy muons leave longer tracks and they produce more light. And at low energies, these tracks can be very short, so short based on the DOM spacing, they can be considered essentially point-like. And there's a lot of difficulty distinguishing between the low energy tracks and cascades. So just an example of what a low energy event would look like. This is something on the order of like 10 GeV. And compared to the images on the last slide, this is significantly less information. So it's much harder to reconstruct accurately what your event looks like. So to deal with this problem, the solution is an upgrade. So the IceCube upgrade is consisting of 7 additional strings that are being added to the DeepCorel area of the detector. Each string is expected to have about 100 DOMs with a higher instrument density, where the vertical spacing is decreased from 7 meters in DeepCorel down to 3 meters. The upgrade will feature 2 new DOM designs, the D-eggs and the M-DOMs. And these new DOMs, the primary feature of these is that they will have multiple PMTs, which is new to IceCube. And then the upgrade is expected to improve the low energy resolution below the lower limit of DeepCorel, around 10 GeV. So some of the current reconstruction methods that we're using most of them are log likelihood based. And then for charge current and mu events, which are the kind of events that I'll be working with specifically, the energy uncertainties are typically in the order of about 15% for the total deposited energy in the detector. The biggest issue that we have with current reconstruction methods right now is speed, because most of these log likelihood reconstructions will take something in the order of seconds to minutes to process an event, which is pretty slow, and especially when you're processing a lot of events. And so this speed issue is one of the reasons we've been looking into neural networks. So my network specifically is a recurrent neural network, which is a machine learning algorithm designed to handle sequential data, which typically just means it has a time relationship. This works well for IceCube because time is one of the primary variables that we have. There are a variety of different applications for RNNs, things like time series forecasting, like stock market predictions. They're used a lot of the time in natural language processing. So this would be things like autocorrect and auto suggestions. You can also do multi-dimensional parameterization, which would be things like recommendation algorithms, like, for example, watching movies on Netflix, and then based on the movies you watched, it'll recommend some new ones to you, and that you can do with an RNN principle. The primary component that's unique to RNNs is the long short-term memory layer, or LSTM layer. And the main function of the LSTM is to weight information in these input sequences based on how correlated it is to the output. So for example, to go back to the example of natural language processing, if I feed it some string that says, I live in Paris and I speak blank, the RNN has the capability to, if I've trained it on enough English, it should recognize first that the blank should be a language. And secondly, it'll understand the context of the word Paris, and then it's associated with things like France, French, Europe, Eiffel Tower, etc. And so it should most of the time correctly predict the missing words, most likely French. And it's the LSTM layer that allows it to do that. We've tried using other neural network architectures in IceCube, for example, CNNs, but there are some issues with that. One of the main reasons is that CNN specifically requires some sort of grid-like pattern, but IceCube is not a grid. It's a hexagon, and it's also not a perfect hexagon. It's a little bit asymmetrical. RNNs don't deal with that issue as much because they are less dependent on the detector geometry, so that is an advantage that it has over other architectures. So to get into the specifics of what I'm using, the original architecture for this was developed for Gen 1 data, the current detector geometry, by another IceCube student named Johannes Wagner. He is now a master's PhD student, I think, at UC Berkeley, formerly at Drexel. So the input arrays are sequences of hits. So it's a time, charge, and some sort of PMT ID for each hit. You feed in these three arrays that all constitute one event that go into the current network architecture. And then one other minor note here is that the input arrays have to be padded or truncated to some specific length based on the processing that we're using. And in this case, they're both front padded and front truncated. So it'll go through this network architecture, and then the outputs that we get are energy and the dx, dy, dz vector components of the direction, and then all of those with error estimates as well. The embedding layer down here can be initialized with the PMT position or orientation. That's not currently used, it's just randomly initialized. Johannes had done studies with this using Gen 1 and initializing with the DOM position, and found that there was little to no improvement between the two different methods. So we've opted for just the random initialization because that's easier. And the biggest factor in this is that the RNN can process events on the order of like 1 event per millisecond, which is 3 to 4 orders of magnitude faster than the LLH reconstructions. So that's kind of the big reason why we're so focused on this research. So the data sample that I'm using, it is simulated charge current new events. So this would all be tracks using the upgrade geometry. We have about 2 million events. The data quality is similar to that we would get from raw IceCube data. There's very minimal processing on this. There is a preliminary noise cleaning applied that uses a clustering algorithm. So it tries to remove individual hits if they're not associated with anything else. And then we're also cutting for the vertex starting in the deep core volume of the detector. So our energy distribution follows a rough power law, highly biased towards low energies, which would make sense because that's the energy range that we're focused on. And then it should be roughly flat in cosine zenith, that's true zenith here, and then approximately flat in azimuth as well. So for energy reconstructions, it's consistently under reconstructing majority of the events at most energies. It's under predicting by about 12% for events between 0 to 10 GeV or so, and then by about 22% up to about 100 GeV. And then roughly 84% of the events are under predicted between 0 to 100 GeV. These dash contours are representing like the 1 sigma spread. The underprediction gets significantly worse at higher true energies. There's a couple of reasons for this. First is that it could be an artifact of the loss function that we're using, mean absolute percentage error. This creates a shoulder in the predicted energy distribution, which is something that we've seen in other neural net studies in IceCube. This could be that the sample is biased towards low energy. So it's more focused on these events and trying to get these right than it is on these events. So it's just kind of ignoring them to some extent. It could also be that the higher energy events have truncated hits. They just had so many hits in that event that based on the limit of that input sequence, it had to chop off some of the information. And so we're not fully seeing all of the energy from that event. And the last thing I want to point out is that a subset of events here are predicted at low energies, regardless of what the true energy is. This is a feature we're really interested in, and I'll dig into more later. One of our initial thoughts is that it could be noise contamination, or that there's something else about these events that just makes them really difficult for the neural net to comprehend. And so kind of the blanket term that we've been using to describe these is non-reconstructible events. To get into the direction reconstructions, the zenith and azimuth median reconstructions are both within a few degrees of the truth, up to about 100 GeV. The 1 sigma bands for zenith are up to about 25 degrees at lower energies, and then up to about 12 degrees at higher energies. And then the azimuth 1 sigma bands are up to about 50 degrees at lower energies, and then up to about 20 degrees or so at 100 GeV. The activity in these off corners of the azimuth distribution here, this 2D histogram, is just due to the phase space of azimuth, the fact that it wraps around at 360. And this phase space is actually difficult for the neural network to learn, which is one of the reasons that we train on dx, dy, dz, and then convert to zenith and azimuth, because the phase space of these is much nicer than these two. And then there's a band of events here at about 240 degrees azimuth. We thought that this might be correspond to the non-reconstructible events from the energy distribution. Now we believe that there are events with high directional uncertainties, and Nathan will dig into this more later when he talks about his work. So from here, we wanted to figure out how well we're doing relative to the kind of reconstructions that we have now. However, there is no official upgrade reconstruction because this is so new. So the best thing that we could come up with was comparing to a current Gen 1 reconstruction that also focuses on low energy. And that is called Osnex Retro Reco, which is log likelihood based. Our reconstruction is the RNN. Both of these are trained with charge current nu track data. We're using the upgrade geometry, they're using Gen 1 geometry. We are dealing with much lower quality data than they are. We have minimal processing, again, the preliminary noise cleaning and the deep core vertex cut. They have much more extensive processing and noise cleaning and quality cuts. And then another big thing to note here is that the Osnex Retro Reco reconstructions are shifted so that the truth will trend, or the predicted will trend along the truth, and ours are not, and I'll explain more about this on the next slide. So basically what this means is that this red contour here representing the median has been shifted from whatever the actual value is such that it trends along the zero line. That's what that means. And that'd be an additive shift for this plot. So what we see is that the upgrade RNN is more accurate at low energies, whereas the retro is more accurate at higher energies. The RNN's 1 sigma bands are smaller than those for retro at most energies. 68% of the events, which would be like the number of events between these two dash contours, are within about 50% error for the RNN at most energies, whereas for retro, this spread is about 75%. Another thing we noticed is that the RNN's median error levels out at a lower energy than retro does. So for the RNN, it's about 5 GeV, whereas for retro, it's about 30 or 40 GeV, so we're in here. Again, it is difficult to make an apples to apples comparison due to the fact that retro's results are shifted. However, you can imagine that if we shifted this up additively by 25%, and then we shifted this up additively by 25%, which would be like tilting the graph by increasing everything by 25%, they might actually be pretty comparable. Then to get into the directional results, the directional reconstructions are much more comparable even with retro shift. Another thing I should note here is that retro is applying a cut so that the cosine at zenith is less than 0.3. This is to remove downgoing events, which are typically have worse reconstructions because we get contamination from muons that are created in the atmosphere that come down and interact on the detector. So this is trying to eliminate some of that background. So the cosine zenith contours and the 2D distribution taper off at the bounds. This is just due to the boundary conditions and how the contours are calculated. You can't actually predict anything above a cosine zenith of 1, therefore everything has to be less than that, which is why this kind of falls off the edges. The RNN shows better true and predicted cosine zenith agreement than retro at higher zenith angles, which again corresponds to those downgoing events. Both reconstructions show really good agreement with the truth value outside of the lowest energies. The RNN's 1 sigma bands are also smaller at lower energies. So for example, the 1 sigma reaches 0.25 at about 10 GeV for the RNN, and then at about 35 GeV for retro. And we see that both RNN and retro show their worst results at the lowest energies, and this should make sense. I talked about this earlier, where these are the events that are hardest to reconstruct because these are the events with the least amount of information to reconstruct them with. And then this segues nicely into the last topic I want to talk about, which is talking about the uncertainty estimates from the RNN. So it actually performs a regression on regression calculation for the uncertainties. So the idea is you start out with your input that gets passed into the RNN. It's trying to predict an energy, for example, to match this true energy, whatever the true energy of the event is. And then it takes these two and combines them into a new truth value, which represents like the magnitude of the prediction error. And then it's trying to predict this as well. So this would be like the uncertainty from the RNN. So just to give a concrete example of this, if the true event energy is 50 GeV, the RNN might predict it at 40. That means that the magnitude of that prediction error should then be 10 GeV, and the RNN might predict this with an uncertainty of 8 GeV. So what that really means is that for this 50 GeV event, the RNN thinks that it is 40 plus or minus 8 GeV. And it does do this for all variables, energy and dx dy dz. I'm only showing energy here for clarity. So why am I telling you all of this? Why is this important? So the events that we saw that were considered non-reconstructible are consistently predicted at low energies, even if the true energy was high. To say this differently, they had a low E pred and a high E true. That means the magnitude of that prediction error should be high, so the uncertainty should be high. So we want to see if we could find features in the energy uncertainty distribution as a function of the predicted energy, again, because the predicted energy is the common factor for all the non-reconstructible events. And when we do that, we see a couple of things. First is that the energy uncertainty is very highly correlated with predicted energy. There's really not much spread at all, which is kind of surprising. And then we see that the events with the lowest median energy uncertainty are predicted at around 2 GeV. And then both these plots highlight a sharp peak in the energy uncertainty at low predicted energies over the range about 0 to 2 in predicted energy, which corresponds nicely to that energy range where we saw the non-reconstructible events from the energy distribution. And so our thought here was that we could use this relationship to develop quality cut from the sample. I think that will lead nicely into Nathan's section of the presentation. So at this point, I will let Nathan take over. Go ahead.
All right, is my audio working?
Yes.
All right, thank you. So hello, I am Nathan Willey. I'm a physics major at Michigan State University as well. And during the past summer, Brandon had been working on this project before, but wanted to hop on a new project. And so I'd worked on this for the past summer up till now. And so I'm going to go into what's been done during that amount of time. And so during that transition, the first thing that was on our minds was, where are these non-reconstructible events coming from, and why are they there? How can we get rid of them, right? And so on the last slide, it had showed that there are events that are predicted at very low energies, but had these huge predicted uncertainties. So it was almost as if the neural network was able to say, I don't know where this goes. I'm going to predict it at 0, but the uncertainty is huge. And so the question is, can we get rid of those events? And will that then get rid of all of our non-reconstructible events that we saw in these weird bands in predicted direction and the weird line in predicted energy? And so here, this plot on the bottom left, the x-axis is the predicted energy and the y-axis is the predicted uncertainty. And this is just illustrating that at around 0 predicted energy, we have this huge spike in uncertainty. And so the idea is we cut any event that has a predicted fractional uncertainty above 200%. And that's what this arrow is showing on the right. Now we're making that cut. And so anything above 200% uncertainty predicted by the RNN is now no longer considered in the final sample. So really what we're doing is we're going back to our sample and cutting out these events from our predictions. And so the thought is, okay, this should be all of our non-reconstructible events. But doing some more digging into the results of the RNN, we found something else strange. So this top left plot is showing now the predicted uncertainty by the RNN in the x direction. And we see that everything looks pretty normal around the lower values. We have a high spike, but once we get to around 0.5 uncertainty, there's this huge spike that seems to make no sense with what the rest of the distribution is showing. And if we go and look at the distribution in just dx, predicted dx, we see there's this huge spike at 0. So once again, the RNN is throwing all of these events into 0 in direction and deciding them a huge uncertainty, as if it has no idea what to do with them. And it turns out, doing some more digging, that the high uncertainty feature appeared in dx, dy, and dz, and also always correlated, or not always, but mostly correlated with a 0 in dx, dy, or dz. So these were all correlated together. So what this means is the RNN has some events that it doesn't know what to do with, and it says, okay, well, you're 0 in x, y, and z, and a high uncertainty. So now the cut we make is if an event has higher than 0.4 uncertainty in every direction, we cut it out. So what this allows us to do is keep any event that maybe just has a high uncertainty in one direction for whatever reason, but also get rid of these events that the RNN just has no idea what to do with. And so that's what this arrow from left to right is showing. We get rid of this cut, which for example, DX allows us to get a much more smooth distribution in the uncertainty. And then if we look in the actual predicted DX, it's much more flat relative to the actual sample. So these, I should say, the orange histograms are showing the predicted, and the blue is just our overall sample. So now doing both of these cuts, we have this high energy cut. We're getting rid of anything the RNN doesn't know what to do with in energy, and we're also getting rid of the events that the RNN doesn't know what to do with in any direction. What happens? The main feature is that these non-reconstructible events that we saw in the predicted energy graph are now gone. This band of events that are thrown into zero predicted energy, regardless of their true energy, that no longer happens. These are cut retroactively. And so what this gives us is now our 1 sigma bands reach the 1-to-1 line for all energies within 0 to 100 GeV. So this makes our overall predictions better by shifting up a little bit. And if we can look at the bottom plots are then just showing the error in bins of 10 GeV, where the error is much more moved to 0 at the lower energies, which is where we're seeing this weirdness happen without the cut. And it's even more noticeable if now we look at direction. If we look at the top plot, which is showing the predicted zenith, we saw in the bottom right this very weird jutting out in the predicted, as if there was some clump of events that were thrown in there. And in terms of the azimuth, we saw this feature around 240 degrees, where the RNN was throwing a bunch of events into that predicted bin. But now if we get rid of any of the events that the RNN predicts that it has no idea what to do with, the arrows on the right show that we get a much better fit along the 1-to-1 line, and there's much less feature-esque things away from the 1-to-1 line, which is much better. So the natural question to ask after you make this cut is, what does the cut look like? What are these events that were non-reconstructible? So if we look at this bottom left plot, the orange histogram is showing our overall sample of events. Brandon showed a plot of this at the beginning of the presentation. This is a histogram in log space. So the blue histogram is now showing what events are cut by this cut. And the main thing to note here is that most of the events that are cut are low energy, very low energy events. And this makes a lot of sense because a low energy event in the detector might have a lack of information, for example. There might be a very few amount of hits that are actually inputted into the RNN. Thus, the RNN might have a hard time reconstructing it. And now the other thing that's very important to note is if an event has a very low number of hits, it could be very highly affected by noise hits. So if maybe 10 other pulses seem to correlate with that event and then part of the event, it's very hard to reconstruct that event as it should be. And this is a result of the fact that our sample isn't very clean in compared to other samples that are used in, for example, the likelihood-based reconstructions. So it's very possible that a much cleaner sample would get rid of this non-reconstructible event problem that we see here. And then the other two plots on this slide are here to show that these cut events don't have any weird features in direction. They're pretty much consistent with the overall sample. And so that is all we did for this cut. That is the most recent thing. One other quick study that I wanted to talk about is at the start of this, or I guess at the beginning of this presentation, Brandon had talked about the fact that when we feed some string of event information into the RNN, we have to either pad or truncate it to fit a certain length that the RNN expects. And so if an event has a lot of hits, there's a question of we're cutting some either beginning or the end of this event's information. Is it important whether we're cutting the beginning or the end of the event's information? And so before, what we were doing is we were cutting always the first hits of the event to then fit the length. So that's what these on the left are showing. And on the right, we did a study where instead we cut the ending event information. And the question was, does this make our predictions any better? And it turns out that not really. There wasn't a huge impact. And one of the main reasons is only 7% of the events are actually truncated, in that it's usually the high energy events that have a lot of hits and thus need to be truncated to fit the length. And so given that we really care about the 100 to GeV range anyway, it ends up being more or less a wash whether we cut at the beginning or the end of the event information. So that is all that I have done. I'll bring us home here with giving us a summary of what me and Brandon have talked about. For the RNN, our energy reconstructions are typically underpredicted by about 12 to 22%, depending on the energy range. This is honestly pretty good, and especially if you compare it to something like the likelihood-based fit, which uses a shift to get it to the one-to-one line, it's very comparable. Our median directional reconstructions are typically within a few degrees, so we're very good at predicting direction. The RNN is showing smaller 1 sigma bands than the current likelihood-based reconstructions across most energies from 0 to 100, which is the range we're looking at. So if we were to do a shift, we would be along the one-to-one line with a smaller 1 sigma band in error. So overall, the RNN is predicting very well. And the events with these high uncertainties that we saw in cut could represent the lower quality events from our data sample that maybe shouldn't be there in the first place. And so cutting out these events allows us to improve the sample quality and also both of our reconstructions that we do in the RNN.
All right, thank you, Nathan. I think that's everything we had. So at this point, thank you for having us, and we are welcome to open up the questions.
Sorry. Yeah, so we have one question from in here.
I have a question on page 29.
Probably have to come closer.
Thank you for the presentation. I have a question on page 29.
Are you able to hear his question?
It's a little quiet.
You said something page 29.
Yeah.
There's a graph on 20.
So on the left top one, why there is 3 lines further?
Yes, so this is representing the median reconstruction in each true energy band. And then these are representing the 1 sigma spread from that median reconstruction. So everything between these 2 dashed lines is representing the central 68% of the events. Does that make more sense?
Actually, I did understand the other 2 lines. What is that?
I'm sorry?
Actually, except the diagonalized one, other 2 line, I did understand what is actually.
Okay, so the central, so this solid red line is the median reconstruction, just every half the events are above, half the events are below. The dashed lines are representing the 1 sigma spread from the median reconstruction. So you would have, let me go back to the retro plots. Yeah, so this is representing where 16% of the events are below this lower line, 84% of the events are below this upper line. So this would be the central, so this would be like 16% here, 34% here, 34% here, and then 16% here. Is that a little clearer?
So
or maybe
percentage means like reconstruction percentage, or what?
Yes, what fraction of the events are reconstructed at these different values in this specific band?
And also one other question is, when energy value is small, there are many like non-constructible events, so we cut it out those data. And it seems like when energy is also goes large, the error size also increasing like linearly. So I'm wondering, is there any particular energy band that relatively has low error size and also have many events we can observe?
That's a good question. So you're saying that at lower energies, we get more events, and at higher energies, these error bars seem to get a little bit larger, right? So is there a band of events where we see a small number or a large number of events, but a small error? And I think the general answer to that is no. I mean, the smallest one that we see, I think, is probably this one. I mean, I guess in true energy, it would most certainly be this one because the range is rather small. For fractional, it appears to be actually, I think they're all fairly comparable in terms of the percent error size. So relative to the number of events, this would be the smallest, but in terms of just the percent error size of these one-step bands, I think they're all fairly comparable.
I had a question relating off that. Usually, I mean, I find that a little odd that the response, is this true in like a regular IceCube analysis with, you know, just regular likelihood approaches, that you find that the errors go like, I don't know, it's like has no features to it. Usually there's like some correlation in energy with error when you have like some detector.
That's a good question. I want to say yes to some extent. It depends a little bit on what your reconstruction is and what energy range you're looking at. But I do believe that there tend to be some features. I guess like I said, it also depends on whether you're looking at the true energy error or the fractional energy error. Yes, I do think there does tend to be a little bit of structure depending on your reconstruction method.
Do you have any other questions from people on the internet at all? Okay, so we see, is anybody raising their hands again? I guess I can have that up. I guess I have one other question to take in. So I understand your approach to calculating errors here, but have you considered using like any other like machine learning based, estimating errors, like some sort of like Bayesian type layers in your architecture? Have you considered anything like that?
No, we have not. This was just the framework that we were handed when Johannes handed off the project to me. But that might be some interesting things that we look into as well.
Yeah, that's it for me. Any last questions at all? Going once, twice. Okay, we'll take the silence as everyone is good then. Great, so thank you very much for the presentation. It's great.
Thank you for having us.
Yeah, absolutely.
Thank you.
Okay, I guess we'll we can all disperse now. Great, thank you very much.